Right, let us show you how to answer an Edexcel paper from 2019. It's paper 2 and it's higher tier. It's worth 60 marks. Question 1. Which of these is the equation for work done? Right, well, work done equals force times by distance moved in the direction of the force. They've tried to catch you out by putting that one there, but that's to do with right angles to direction of force, so that's wrong. Part B. A ball has a mass of 0.046 kilograms, so that's our mass M. Calculate the change in gravitational potential energy, so change in GPE is our target, when the ball is lifted through a vertical height of 2.05 metres, so that's height h. And they've kindly gave us the equation, so we'll just pop the numbers in. We don't need to rearrange it. 0.046 kilograms times by gravity on Earth. Right, they haven't gave you the gravity, so you need to know that gravity is 10 newtons per kilogram, and multiply that by the height, which was 2.05 metres. And that comes out as 0.943. They've done it to 3 decimal places, so we'll do it to 3 decimal places. Part 2. The ball is released. Calculate the kinetic energy of the ball when the speed of the ball is 3.5 metres per second. So kinetic energy equals a half times by the mass times by the velocity squared. So if we pop the numbers in, it's a half times by the mass was 0.046 kilograms, and the speed of the ball, the velocity, is 3.5. Remember to square that. And that comes out as 0.28175. And we'll just leave that as 0.28. Part 3. The ball bounces several times. Figure 1 shows how the height of the ball above the floor changes with time. Right, yeah, there's your time, there's the height of the ball. Use figure 1 to estimate the maximum height that the ball reaches after the first bounce. So that's the first bounce there, and that's the maximum height there. Right, so they've took the bottom of the ball as being the measurement, so we'll take the bottom of the ball as well. So if that's 0.5, that'll be 0.6, 7, 8, 9 and 1. So that's 0.85. Meters. Part 4. Explain why the ball does not bounce back to its starting height of 2.05 metres. Right, well, as the ball hits the floor, it's going to lose energy as sound and heat to the surroundings. I would always be saying those 3 things, even though it's only worth 2 marks. Question 2. Which of these symbols is used to represent a thermistor in an electrical circuit? Right, that's a diode, that's an LDR, that's a motor, and that is the thermistor. So the answer is D. Part B. A student investigates how the current in a lamp changes with the potential difference across the lamp. Remember, that's just voltage. The student uses the results to calculate the resistance of the lamp. So current I, resistance is R. The results are shown in the table in figure 2. Right, one value of resistance is missing from the table. Calculate the value of resistance that's missing from the table. Okay, so V equals I times by R. So therefore, if we pop that in a magic triangle, I times by R would go on the bottom, V would go on the top. Cover up what you're looking for, which is resistance, and that leaves V over I. So R equals V divided by I. So voltage divided by current. So the voltage is 5.0 and the current was 0.26. And when you do that, it comes out as 19.23 ohms. Now they're all just rounded off to 0 decimal places, so we'll just round ours. Does 19 seem to fit the pattern? Yes, it does. Okay, so that's great. Always double check. Part 2. The student writes this conclusion. The resistance of the lamp is directly proportional to the potential difference. So that's the voltage and the resistance. Comment on the student's conclusion. Use information from figure 2 in your answer. So we need to look at resistance and voltage. Let's go back to the table. So resistance and voltage. Now the easiest way of telling if something's directly proportional is if one thing doubles, the other thing should double. So when the voltage doubles from 2 to 4, did the resistance double from 14 and it should go up to 28? Well, no, it didn't. And let's just double check. What about when it doubles from 3 to 6? Did the resistance double? So 17 should double to 34, and it does not. So it's not directly proportional. As the voltage increases, the resistance increases, but it's not directly proportional because as one thing doubles, the other didn't double. As voltage increases, R increases, however, not directly proportional, because as V doubles, R did not double. And then use some information. Example, when it went from 2 volts to 4 volts, it did not go from 14 to 28. When voltage doubled from 2 volts to 4 volts, resistance did not double from 14 ohms to 28 ohms. And that's how I encourage my students to respond whenever they're asked about directly proportional results. Part 3. The student used a power supply that had fixed output voltage settings. Each of these outputs was a whole number of volts. Describe how the student could add a component to the circuit that would provide a continuously variable voltage across the lamp. Right, you need to add a variable resistor and it needs to be in series with the lamp. Question 3. A student uses a plotting compass to investigate the magnetic field around a wire. Figure 3 shows the wire going straight through a card. Figure 3 shows the compass needle when there is no current in the wire. Right, so we can say it's pointing that way. Which of these shows a possible direction of the compass needle when there is a current in the wire going from P to Q? Right, if it's going from P to Q, that means it's going up. Now, if we use the right hand grip rule, now point your thumb upwards which way the current's going, and your knuckles will sort of be like that, and your fingers will come curling round like that. This is a horrible picture. I'm useless at drawing, sorry. So the current's going up, and the magnetic field is represented by the fingers, which is going anti-clockwise. So if the magnetic field is going anti-clockwise, that way, this needle is going to be pointing that direction there. The magnetic field will be going round anti-clockwise. Part 2. Describe how the student could develop the investigation to find the shape of the magnetic field produced by the current. The shape. Right. 3 marks. What they'll need to do, if you're using the same compass, if you move the compass over to here and turn the current on, and then you'll see which way the compass is pointing, and then move the compass to where the needle's just been pointing and find out which way it's going again, and keep on moving the compass and keep on either putting a dot which way the compass is pointing, move the compass again to the dot, move the compass there, then draw another dot, then move the compass to that dot, and go like that, and keep on going. And then you can connect all the dots together, and that'll show you the shape. If you do get another question and it says show the direction, you do exactly the same thing, but instead of just drawing a dot, you'd obviously just draw the arrow and then connect all the arrows in the same way, and it'll show you the shape and the direction. Right, how do we say that then? So record the magnetic field at a point. Move the compass to a new position. Draw a dot at the new position. Repeat this around the wire. Connect the dots to show the shape of the magnetic field. So you'll definitely get 3 marks for that. The other way of doing it is if you use multiple compasses all at the same time and just put dots at the end of each arrow on the needle and then connect them. Or just because we're looking for the shape only, you could sprinkle iron filings, then turn the current on, and then give the card a little bit of a tap, and the iron filings will align themselves with the shape of the magnetic field. So 1 mark for that, 1 mark for that, 1 mark for that. That's your 3 marks. That might be easier to say just to get the 3 marks. Or sprinkle iron filings on the card. Turn the current on. Tap the card. Iron filings will line up to show the shape of the magnetic field. So if you've said any of that, well done. Part B. Figure 4 shows a copper wire between 2 magnetic poles. The current in the wire is in the direction shown by the arrow. There you are. The wire experiences a force due to the magnetic field. The direction of the force due to the magnetic field is... Right, this is Flemmings' left-hand motor rule. Now in England, which is where I am, we motor on the left-hand side of the road. So this is how I tell my students to remember it. If you look at your left hand, your thumb represents the movement, in this case of the wire. The first finger at 90 degrees. First finger tells you the magnetic field, and the second finger, and they're all at 90 degrees to each other. The second finger shows you the direction of the current. Now that's conventional current, from positive to negative. And the magnetic field goes from knuckles is north, fingertips is south. So that shows you going from north to south. So now we need to line that up. So the second finger is going that way. The magnetic field is going from north to south that way, which means that the movement of the wire is going to go up. So the answer is B. Now it's only worth 1 mark on this paper, but I've saw that worth 6 marks, so I have explained everything to you. You'll get marks for saying what each thumb or finger represents, which direction it's pointing, and saying that they're all at 90 degrees to each other. I've got a nice video all to do with Flemmings left-hand motor rule if you need more help. Check it out on my channel. Part 2. The interaction between the magnetic fields produced by the magnet and the current in the wire produces forces on the magnet and the wire. Compare these two forces. Well, they'll be equal in size but opposite in direction. So what they mean is that the magnet is putting a force on the wire upwards, and at the same time the wire will be putting a force on the magnet downwards. They'll be equal in size but opposite in direction. The reason why the magnet doesn't move is because it'll be sitting on a table. Plus the magnet's a lot bigger and heavier than the wire, so you'll easily see the wire move. Part 3. Figure 5 shows a different wire inside a uniform magnetic field. So uniform just means equidistant apart. The magnetic flux density of the magnetic field is 0.72, right, so that's B, magnetic flux density. The length of the wire inside the magnetic field is 30 millimeters. Right, this is a problem, because that's in meters and that's in millimeters. So we'll need to convert that. So it's L for length, and it'll be 30 millimeters, and we need to divide that by 1,000, because there are 1,000 millimeters in a meter. So that'll equal 0.03 meters. The size of the force due to the magnetic field on the wire is 0.045 newtons, so that's F. Calculate the size of the current in the wire. So the current I is our target. Use an equation selected from the list of equations at the end of the paper. Right, so we're looking for an equation that's got B, F, L and I in it. Right, here it is. Force on a conductor at right angles to a magnetic field carrying a current is magnetic flux density times by current times by length. In other words, F equals BIL. Or as we say, F equals Bill. So F equals Bill. And we're looking for the current. So magic triangle. Make the magic triangle nice and wide on the bottom, because we're going to need something times by something times by something. So do your top shelf as a divide by sign, and then put 2 multiplied signs. So B times by I times by L goes in there, and then 1 space and 1 thing, so F must go on the top. Now cover up what you're looking for. So we're looking for I. So cover up I. What we're left with? F divided by B times by L. So therefore I equals F divided by B times by L. Pop the numbers in. Make sure you use your converted length, and that equals 2.083, and we'll round that down to 2 decimal places. We could have left it to 3 decimal places because they gave us one of the numbers to 3 decimal places. Question 4. A student measures the density of glass. The student has a bag of marbles all made from the same type of glass, a weigh and balance, and a plastic measuring cylinder containing water. Describe how the student could find, as accurately as possible, the density of the glass used for the marbles. So as I say to my students, base your explanation on a calculation. So the calculation we need is for density. So density equals mass divided by volume. So you just need to tell the examiner to measure the mass. Now if we want it as accurately as possible, if we measure the mass of 10 marbles and then divide by 10, we'll get a good average. Now what are we going to measure the mass with? With a mass top pan balance. And we also need to measure the volume. And again, if we do it of 10 marbles and then divide by 10. Now, how are we going to do that? Right, probably the easiest way of doing it is if we get a measuring cylinder and we'll fill that up with water. And then we'll add the marbles. Or rather half fill that with water, and then when you add the marbles in, the volume's going to increase, and then the volume of the marbles will be the difference, or how much water we've displaced. Pop another couple of marbles in there so it's accurate with the 10 marbles. And to be honest, that's worth 4, but we could easily get 6 marks for what we've just said there, just in case that's the 6 marker for you this year. Instead of using the measuring cylinder method, you could have used the displacement canister method, which would be to fill the displacement can with water, again have a measuring cylinder there, and then when you pop the marbles into the displacement canister, the water comes out, and how much water gets displaced, that's the volume of the marbles. So it's similar to what that was saying down there. Part B. A beaker contains 0.25 kilograms of water at room temperature, so that's mass. The beaker of water is heated until the water reaches boiling point 100 degrees C. So that's the final temperature. The specific heat capacity of water is 4,200 joules per kilogram to make it heat up by 1 degree C. So that value is called C. The total amount of thermal energy supplied to the water is 84,000 joules. So that's Q, the heat energy. Calculate the temperature of the water before it was heated. So we're looking for the start temperature. Use an equation selected from the list of equations at the end of this paper. So we're looking for something that's got mass, M, Q, C, and the change in temperatures is delta Q. Right, so it's this one that we want. change in thermal energy equals mass times by specific heat capacity times by change in temperature. So delta Q equals mc delta theta. Delta Q, so change in heat energy, equals the mass times by the specific heat capacity times by the change in the temperature. And we're looking to calculate the temperature of the water before it was heated. So we'll need to rearrange it to get delta Q. So magic triangle, but nice and wide on the bottom again. Do a top shelf, that's our divide by sign, and 2 multiplied signs. So mass times by specific heat capacity times by change in temperature goes in here, and one space and one thing, so delta Q must go on the top. Cover up what you're looking for, so we're looking for delta theta, the change in temperature. What have we left with? Delta Q divided by m times by c. So therefore delta theta, change in temperature, equals the change in the heat energy divided by mass times by specific heat capacity. Right, let's pop the numbers in. So the change in the energy was 84,000 joules. Divide that by the mass, which was 0.25 kilograms. Multiply that by the specific heat capacity, which is, for water, it's always 4,200 joules per kilogram degrees C. If you can memorise that number a little bit, that's great. And that comes out as 80 degrees C. Now, that's not the temperature it was at the start, that's the change in temperature. So if it was 100 degrees at the end, we need to take that away to get what the temperature was at the start. So the change in the temperature is going to be the final temperature, take away the initial temperature, the start temperature. So if we rearrange that, so therefore, initial temperature is going to equal the final temperature, take away the change in temperature. So that's going to be 100 degrees C, take away 80 degrees C, which is going to be 20 degrees C. That's quite a lot of work there just for 3 marks. But it is what it is. You do know that you'd literally get 3 marks just for putting the answer. So you don't necessarily have to show all of this working out. I'm just trying to teach you how to do it properly, so I'm showing you how I would do it, just to make sure that you understand it properly. Part 2. The heating continues until 0.15 kilograms of the water has turned into steam. The thermal energy needed to turn the boiling water into steam is 0.34 megajoules. So that's our heat energy. Calculate the specific latent heat of vaporization of water. Now that's what we call L. Use an equation selected from the list of equations at the end of the paper. And that's M, our mass. So we're looking for an equation with M, L and Q in it. Right, here it is. Thermal energy for a change of state equals mass times by specific latent heat. Q equals M times by L. And we're trying to get L. So let's rearrange the equation using a magic triangle. M times by L will go in the bottom here. And then one space and one thing, so Q will go on the top. Cover up what you're looking for. We're looking for L. What we're left with, Q divided by M. So L equals Q divided by M. Let's pop the numbers in. Now, do I need to rearrange the equation? Are we okay leaving it in megajoules? Yes, the one it left in megajoules. So 0.34 megajoules divided by the mass, which was 0.15 kilograms. And that comes out as 2.26 recurrent, which is 2.27. And I've left it to 2 decimal places because they've gave us both their numbers to 2 decimal places. Now watch what I show you here. Watch this tip. You know how you had to use an equation selected from the list of equations at the end of the paper? Well, if you sometimes look at the units, it'll actually tell you what to do with the numbers. That is megajoules per kilogram. So if you literally took those megajoules and divided it by that kilogram, that is basically what you needed to do. So you could save yourself the hassle of looking the equations up. Now that doesn't work all the time, but it is a good tip to help you for sometimes. Because if we did megajoules divided by kilograms, that's exactly what they were looking for. Part 3. The graph in figure 6 shows how the volume of 1 kilogram of water changes with temperature. Describe how the density of water changes with temperature over the range of temperatures shown in figure 6. Calculations are not required. Okay, so we don't need to use the actual numbers. However, I am going to base my explanation on a calculation. So to get the density, rho, you do the mass divided by the volume. Now the mass is going to stay the same, 1 kilogram. So if the mass is constant, the density is going to be proportional to 1 over the volume. Now that basically means if the volume gets bigger, the density is going to get smaller, and also, that's the proportional sign by the way, if the volume gets smaller, the density is going to get bigger. So let's have a little look and see what's happening. Right, between 0 degrees C and 4 degrees C, we've got the volume is decreasing. The volume decreases. Then we've got the minimum volume at a temperature of 4 degrees C, and then from 4 degrees C up to 11 degrees C, the volume is increasing. But they've been a little bit tricky because they don't want us to talk about volume, they want us to talk about density. And the way that we relate the volume to the density is with this equation, as I've said. So between 0 degrees C and 4 degrees C, the volume's decreasing. So the volume decreases, that means that the density is increasing. So density increases. When you've got the minimum volume, that means you're going to have the maximum density at 4 degrees. And then if the volume increases, that means that the density is decreasing. So that between 4 degrees C and 11 degrees C, the density is going to decrease. So let's just write that down. Between 0 to 4 degrees C, density increases. At 4 degrees C, density is maximum. And then from 4 degrees C to 11 degrees C, density decreases. So we'd get 3 marks for that, and it's only worth 2, so we've easily got the marks. I hope you've understood that. Question 5. Figure 7 shows an athlete using a fitness device. The athlete stretches the spring in the device by pulling the handles apart. The spring constant in the spring is 140 newtons per metre. Spring constant has got the symbol K. The athlete does 45 joules of work to extend the spring. So work is the same as energy transferred, E. The athlete takes 0.6 seconds, so that's the time T, to expand the spring. Calculate the useful power output, so we're looking for P of the athlete when stretching the spring. So what equation do you know that relates power, energy, time and spring constant, or at least some of them? Well, we know that power equals the energy transferred, or the work you've done, divided by the time taken. So P equals E over T. So I'll just pop those values in. The energy was 45 joules and the time was 0.6 seconds. And that equals exactly 75. And that'll be watts, because it's power. Part 2. Calculate the extension of the spring. So that's X is our target. Use an equation selected from the list of equations at the end of this paper. So we've got K, E, T, X. Let's see what we've got. Right, here it is, hiding right down the bottom. Energy transferred in stretching equals 1/2 times by spring constant times by extension squared. E equals 1/2 times by K times by X squared. Right, we're going to have to rearrange that to get X. So if I do a magic triangle, and once again we need to have 3 things on the bottom. So 1/2 times by K times by X squared is going to go on the bottom, and E is going to go on the top. Cover up what we're looking for, so we're looking for X squared, and what do we get left with? E divided by 1/2 times by K. Now we don't want X squared, we want X, so we need to square root both sides. And by square rooting both sides, it obviously gets rid of the square on the left. Right, let's pop the numbers in. The energy was 45 joules. K was 140 newtons per metre. Now remember, you type in 1/2 into your calculator by doing 0.5. And that comes out as 0.80. Question B. A student investigates the stretching of a long piece of rubber. Figure 8 shows the apparatus to be used. The student puts just enough weight on the weight hanger to make the piece of rubber just tight. The student wants to plot a graph to show how the extension of the piece of rubber varies with the force used to stretch it. The student adds a known weight to the weight hanger. Describe how the student could measure the extension of the rubber when he adds another weight to the weight hanger. Right, well, if he measures the length of the rubber and then he adds the weight on and then he remeasures the length of the rubber, and how much it's extended is the difference in lengths. measure the length of rubber, add another weight, remeasure the length of rubber. The extension is the difference in length. Don't just say the extension is the difference. Make sure you say in length. Now it's only worth 2 marks, so we'll definitely get 2 marks for saying that. Part 2. The student obtains a series of values of force and extension while loading the piece of rubber and then unloading it. Figure 9 shows the graph of the student's values. So the force is up the sides as he's loading it, and it shows you the extension, and then as he's unloading it, it comes down a different way. Explain how the shape of this graph shows that the distortion of the piece of rubber being stretched is different from the distortion of a spring being stretched. Well, if you had a spring being stretched and you had force up the side and extension along the bottom, you just get a straight line, as long as you didn't exceed the elastic limit, of course. And then if you unloaded it, it would just come straight back down the same way it went up. So how do we write that? This is linear and that is non-linear. So I think that's a good way of describing it. Question C. The area between the curve and the extension axis of a force extension graph corresponds to work done or energy transferred. So area between the curve and the extension axis, it's work done or energy transferred. Suggest what the shaded area of the graph in figure 9 represents. Right. So as you're loading the graph, they're saying that the area between the curve and the extension axis, well, this is the extension axis, so all of this red area here, that represents the work done as you are loading it. Now, this area here, as you're unloading it, was the work that you did as you unloaded it. So what they're saying is, what's this shaded area? Well, that'll basically be the difference in energy between loading and unloading. Now, where did that energy go to? Well, when you stretch a rubber band, it gets hot. So the energy lost will be thermal energy that's gone into the rubber band and then gets lost to the surroundings. So how do we write that? So the shaded area is the difference in energy transferred, or work done, between loading and unloading. This energy is thermal energy lost to the surroundings. Now that's quite a tricky question because it doesn't come up all that often. Question 6. Figure 10 shows 2 electrical devices for heating water. Right, immersion heater from a battery and a kettle connected to the main supply. The current in the element of the immersion heater is 14 amps. So that's I, immersion heater, that's 14 amps. The power of the immersion heater is 130 watts. Calculate the resistance. So R is our target. That's P of the immersion heater. give your answer to two significant figures. Right, what equation do you know that connects I, P and R? Well, P equals I squared times by R. Put that in a magic triangle. Top shelf, divide by I squared, and R would go on the bottom, and then P would go on the top. Cover up what you're looking for, so R, and what we're left with is P divided by I squared. So that's 130 watts divided by 14 squared. That's the amps, and that equals 0.663. And it wants it to two significant figures. So 0 is not a significant figure, so there's one significant figure, two significant figures. Does the 3 round the 6 up? No, it does not. So the answer is 0.66 to two significant figures. Part 2. The current in the heating element of the kettle is 8.3 amps. So the kettle current is 8.3 amps. Now it said that the immersion heater was 14 amps. State two differences between the movement of charge in the heating element of the kettle and the movement of charge in the immersion heater. Right. Well, the charge is the electrons. And in the kettle is connected to the mains supply, and that is AC. So the electrons in the wire go forwards for a split second, then they go backwards because it's alternating current. The immersion heater is a battery which is DC, so the electrons just flow in one direction. And if the current's only 8.3 amps, that means that it's going to be a lower amount of charge flowing per second compared to the battery, which will have a higher amount of charge or electrons flowing per second. So how do we write that? So the rate of flow of charge, or the movement of charge in the kettle, is less than the rate of flow in the immersion heater. The reason I added movement of charge there is because try to use the same words that they do. And the direction of the flow of charge in the kettle keeps changing. So it alternates, and that's because it's AC. The heater was DC, direct current, and the movement of charge flows in one direction. So they're checking to make sure you know the difference between how electrons flow in alternating current compared to direct current. And also they're checking to make sure that you know that it's direct current that comes from a battery and alternating current that comes from the mains. Part B, final question, our 6-mark question. Figure 11 shows the 3-pin plug used to connect the kettle to the mains. Right, they've specifically talked about the earth pin and the fuse. A fault occurs in the kettle, causing the live wire to touch the metal case of the kettle. Explain how the safety features of the plug operate when this fault occurs. Right, that's exactly what the earth pin's about. If the live wire becomes loose and touches the metal casing, and you touch it, it'll cause a shock. So the earth works with the fuse in order to turn off the current. I'll show you what I mean. If you look inside a kettle, it'll have a circle of resistance wire. Now if you've got the kettle here, there's the spout, there's the handle. Now if the kettle's working properly, the current will go all the way around that resistance wire. However, if this live wire, which is brown, becomes loose, the current won't flow around all that resistance. And what will happen is it touches the metal casing instead, and then the whole kettle will become live when you touch it. If you've already got an earth wire, what will happen is the current will go through the live wire, then it'll go through the earth wire, and it'll go back up to where the fuse is. So the resistance in this circuit is less, which means the current will be more. And if the current's more, it'll blow the fuse. And it'll switch everything off and protect you. I have got a lovely video that explains all that. Right, I'll show you what to put for 6 marks. So first talk about the earth wire. So it's connected to the metal case. Now if it was a plastic case, you wouldn't even need it. It's connected to the metal case because the metal case is a conductor. When the live wire touches the metal case, resistance decreases. It's what we basically call a short circuit. And if you've ever heard the word short circuit, you'll know what it means now, because instead of going right the way around the long circuit, now it's just created a short circuit. So it's short. It's like a shortcut. It's not going all the way around anymore. It's just going up and coming straight back. So now if we start talking about the fuse, the current will increase. That's because the resistance decreased. So the fuse wire will get hot. Fuse is a thin wire. So the fuse wire gets hot because there's more current in there. It blows, turns off the circuit, and that protects the user and stops fires. Protects the user from electric shock and prevents fires. Right, there's loads of stuff there. You'll definitely get 6 marks. Once again, the more of these papers you practice, you will definitely get better. So I hope you feel as though you've learnt loads of stuff there. Best of luck in your exams. Work hard and be nice. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.